Hello, everybody. My name's Kelly Swanson. I'm a citizen scientist, and this is Darklight. For this session, I'm going to be working with M87, which is a large black hole. So, some researchers have done some articles on this recently, and M87 is considered to be one of the first imaged black holes, because it was officially imaged and accepted. The problem with black holes and how they lose their energy is just based on research. There's um, there's very little visual evidence of what a black hole looks like, functions, or does at all. They see radio data. They simulate this data that it's received back from telescopes. And through these chemical simulations and these computer simulations, they get an idea of what they expect it to do based on what the data says it did. So, one of the first items that I ever did was go directly to the most famous black hole picture out there and redevelop it. And when I posted it up on social media, very few people paid any attention to it, which made me question whether or not people were really all that interested in it, or it was just an exercise in futility. Um, but I've looked at many black holes with dark light, and they all have the exact same pattern. They all exhibit the same functionality, and they all have trademark colors along with trademark standard behavior, if you know what I mean. They do the same things. And there are different types of black holes. Just like there are different stars, different planets, different galaxies, different formations in our universe, there are different ways that a black hole can come together. And based on that, I've classified several different ones. I've published some of these findings on my website, and while it hasn't been put into an actual document that I've published yet, I've written lots of documents about them. I just am not affiliated with the university or anything like that where I would feel there would even be a need to publish them. Um, no one really looks at citizen scientists that much unless you are attached to somebody of popularity. So I figured, what's the point? No one gives a shit. So that's been my take on it until now. Now I just don't care. And I'd rather put it out there in the world than embarrass all these scientists, because I figure, well, if they're not going to listen to me anyways, who cares? So I'm going to show you exactly what's at the heart of M87 right now. So one of the fundamental filters that I use is dark night, and it's just simply designed with Gaia. Um, I use data from Chandra X-ray Observatory, and I also use data from the Hubble. And with the methodology that I developed and invented with my co-conspirator Sir Isaac Newton in his book Optics, I figured out a formula and formulae that work very, very well for peeking through the dust and debris and matter that's out there in the universe that has sort of baffled our, scientists that we have here on planet Earth. This one right here is called Energy Level 1. This is a filter that uses a math formula very much like the Balmer series of edge detection. And I can utilize this to kind of spread away, smooth out certain areas while focusing in on the details of other areas, as you can see here. My main goal for these filters was measurement. I wanted to be able to accurately measure the universe with a visual acuity that was far better than guessing with a blue shift or a red shift. The main thing was to see it visually, to peer through the ocean that is the universe and use a special type of flashlight. As you can see here, M87 is one big circle. In the center, there are 3 objects of main importance. And I'll take you in a little closer so you can see the jet and how this fold works. So, a black hole is not like what you would see in the movies. I've identified black holes and I've put them out and published them so that some of the people like Kip Thorne could take a look and see what he saw in the movie being generated in real life. And, it goes without saying, there's so many different complexities to the universe that it didn't surprise me that black holes were included among these complexities, and not just the generality of being a black hole, but looking differently based on how the black hole occurred. The one thing that always stays true to a black hole is the vortex, the turbine-like tornado spinning, corona bending vortex. And it is a mathematical wonder because it can be replicated in math, really straightforward. One of the tie-ins to the black hole is our knowledge of stars. Well, my knowledge of stars. The main aspect of a black hole is the formation. How it's formed will be the deciding factor on how it functions. And I would just want to show this to you, as you can see here. You saw the image pop up the way it did. That's one of the benefits of DARKLIght, is that it does a whole image scan, because the prisms don't care. They go right through any frequencies, and sometimes Adobe's AI kind of freaks out and shows me a glimmer of what's inside or what's available, like, oh, whoa, because the filters take a little bit to load. There's layers and layers. Some of my filters have over 500 layers in them. Some of them have over 1,000 layers in them. And they've all been mathematically sorted in order to focus where I want that light to focus. In the beginning, I did it manually by adding in multiple layers. But as time went on, I started to build a repertoire of functions within the filters themselves, so I kind of knew exactly what was going on and what I needed to slide, positive or negatively through the spectrums. And I was able to start visually building my filters. And from that point on, I've been visually building them. And right now we have over 400 in our series of filters, and they're broken down based on the telescopes that have been utilized to bring all of these filters to fruition. As you can see here, just a simple adjustment of exposure goes in pretty deep into the system. And without these filters, you can't do this. You can try, you can get close, but you're not really digging in as deep as you can when you use an achromatism filter. And that's just the fact of the matter. Just like you can't see closer unless you use a pair of glasses. You can't see in the dark unless you turn on a light. It's as simple as that. So as I turn the exposure down, you're seeing more visual light, and you're seeing things get pushed away and developed. The filters themselves function just simply based on the formulas that Newton created in his book, but then I've taken and made them better, made them more modern, so that us as the viewer and user could get more creative use out of them. Because unlike having a laboratory with like 5 or 6 prisms in it, it's much better to have 1,000 prisms and they each do a function that you can control. You'll notice the processing time. So while I'm recording this, I'm actually moving the controls. And there is a delay in the processing because it has to calculate and catch up and do that to every single layer I'm telling it to do it to. And I'll show you what a processed layer looks like. Yeah, it's a good function point. So what's beautiful about Lightroom is the way it deals with layers. So as I build layers, my layers aren't typically just layers within like one image or another. They tend to be specific points within the image. And when I launch the filter, it will go through and scan based on those layers that I designed. And it will point out certain portions of the image that it found, which was one of the really neat features of Lightroom's AI, is that it can do a little preliminary precursor investigation to get into the weeds of your image. And it just does that by visual acuity. It just sees the tones change within the image, and it sees and it compares the pixels just like any good math problem would. And so I was able to use the strengths by paying attention to what was going on in the beta process of this. And then from that point on, I was able to learn by doing it, basically learn by osmosis. You got to get in and actually work with the masks and work with the filters and adjust them at such a small amount that you see what's happening. Certain filters have one color range selected, whereas other filters may have a luminance range. And then let's see if we can find one of the bigger, deeper masks. It might be down lower here, down into the weeds. Looks like we're at symbols right now. And there are features within the masks that aren't even viewable in the image, which I use them to find. Here's one where it decided that it used luminance and has different copies within there to illuminate certain features within the image itself, but focus that luminance just on that item, because it may be lesser or greater than the rest of the image. But the whole principle behind DARKLIght is to take unvisible items that are out of the visible spectrum and bring them into the visible spectrum. So you literally have to compensate for the lack of darkness or the lack of brightness in an image in order to tone it back. That's why some of the images they look so bland in some cases, and then in others they look three-dimensional and vibrant. Colors at the very base level, according to Newton, were just very basic. Once you started breaking things apart, they generally went back to their base colors, red, magenta, blue, violet, yellow, white, darkness, which is a tone of purple and red and black. It just drifts off into nothingness. And so what I'm seeing in here, I started noticing that a lot of the spectral colors match the spectral atomic colors that you would see in spectrographic element experiments. And so I started matching up the frequencies with these, because in some cases they show up just as they are in a lab being put under extreme energy and heat, such as hydrogen and nitrogen, and even Berkeleyan and Americium and all these others that I can't pronounce all the way. So looking at some of these images, it's almost like looking at an X-ray, because you can pick apart just an area that you want to see and find out what it's doing, where it's roving around in the image, and then you can make adjustments to it based on that knowledge, based on what you want to try to refine. When you can't find an area within your mask, you can go into the mask itself, select a color range, and then find a point where you want to say, hey, I want to see this. Now, one of the things that I noticed when I zoomed in here was, of course, this shape, and this shape. This shape is very important. This shape has one circle here and one circle here that we're looking down on. So when I see things that are shaped like this, I've seen them before in other universe portions of our universe, images, and that drives my curiosity. So when I select this, it's going to show me the color range, which is blue. So it matches the color range that I've seen in some of the other areas. And we're going to highlight this area with the mask as we get down here. And it's going to take it a bit to show the overlay. But we're going to refine this down. And this is where you'll start to see the shadows you can't see within your image, because it's going to light up the areas in red, and it's going to show an overlay, and it will use that red overlay depending upon how much refinement you do to show you where objects are that may be out of focus or just out of range within the visible spectrum. And we're doing this just on one area. We can go around and we can select different areas, and it will highlight those areas or select those areas and keep the same color range and mask amount that you may or may not have selected. And again, it takes a bit for it to process, so you kind of have to wait for it to catch up, which is what we're going to do right now. So now we see it adjust based on where we touched. And there's light passing underneath and through the middle and around to the other side. So let's see what's in this dark spot right here in the middle. to come up. It's pretty bright. So that object is emitting from back here, or back there is pulling that object backwards. You can notice now in the center it's kind of a pinkish hue as it's shining from there, so we know that's hollow right through that area. So I'm going to select this. There's also a dark area right in here, and there seems to be a light in a dark area ring right around this area here. And yeah, this red is matching this red, and it's matching this red. So there's this dark shadow right in here, along with this shadow. And this, again, this flat spot over here is still there. And you notice the triangulation in the middle. Very much looks like a star. Let this catch up one more time. And then we're going to drop the exposure in this. The other thing we're going to do while we're here is we're going to minimize the texture, which works as a refinement on the focus, surprisingly enough. We're also going to reduce the clarity because the distance here is so far away. We don't want to overpower the brightness that's pixelating this right now, because it's showing a shape, but we want to bring that shape out, and the more refinement that we do in that area will help us later on. Now with this mask, the light has been adjusted up, so we're going to duplicate this color range to essentially double the effect of what we've done. And then we're going to duplicate it a third time because I want to. And so now bring the exposure up just to see what effect this has on it. And then we will move this top selection. So we duplicated the settings 3 times, and the settings will match all the 3 areas that we did. But by touching a different spot, we're spreading out the settings across the image so that that same setting can be utilized in a different spot. And it's kind of like doubling up on your capabilities, but throughout an entire image. So when we back out here of where we're at, by adjusting that center image, we're adjusting the entire image because it all is kind of tuned within your whole image. The frequencies of the colors match those that we've selected in other parts. So when we touch the color of, say, a black hole portion, you might actually see something light up over here that mimics that same frequency, but yet it didn't here and it didn't here. But it certainly did it up here by this star, which I found to be true more often than not. So the other thing I like to do is to adjust after I've zoomed out, just to see what overall effect that might have. You know, might make something more detailed. You might be able to reduce down some noise so that you can zoom into a small area, and of course you got to wait for it to catch up, but to see what it displays. So it's even showing full particles inside that, which is always fun to see. It's fun to see these little bits and bobs and know that these things are humongous. In most cases, they're bigger than our Milky Way. So when you're adjusting the masks, for instance, say you select this mask here, which is an illuminance range, you can go in and you can adjust the mask itself and see how much the effect will have on it. Just by adjusting the luminance range, you can suck the life out of a picture, or you can add more luminance throughout the entire image, just like this. We'll wait for it to catch up. You'll also notice, and I find it in many images, where image transition lines, like bombers or Pouchel or it's not Baxter. What is it called? Balmer? Pouchel. And those are the big ones. The Balmer series of hydrogen emission lines are everywhere in an image. But one thing I do see all the time is this grid. I see these grids in certain areas of imagery that focus around energy. And where I see them stand out the most is in areas where two energy sources are competing. And it's almost as if we're looking at gravitational disturbances, literally forces of energy fighting one another to pull apart one another, or to push two parts together. But it's usually, in any case, it's a blending possibility. It's where things are getting blended. And you can see there's a disruption right here, along with this, competing with this monster. And there's little edges all around this edge right here. And there's squares in this. And it's just in this area over here, and a little bit over here, but not so much over here. So, really interesting things, you know. Once you start delving into this view of an object in our universe, you really get to see a whole new visual way of seeing the universe. And that was really my goal. My theory was that we weren't seeing everything we possibly could see, Thus, we wouldn't be able to see the interactions, and so we're missing out on those alone, which makes it really stupendous. It also, it's like having a new car. After you get a new paint job, you've got a 20-year-old car, and voila, it turns, the Event Horizon into an amazing telescope. It turns the Hubble into a powerful telescope. It turns James Webb Space Telescope into the mightiest of mighty. And now with Euclid, DARKLIght really shows detail down to large objects, and it's fun to use. It really is. I've used it now. I'm on my 5th year, and it has helped me understand the universe so much better. Just testing things, reading papers, and looking at work that others have done, and then either challenging that notion that they came out with, or they left something open for possible future study, and I go in and I'm like, hey, this is what DARKLIght can do. They want to see inside M87. Okay, let's go take a look and see how close we can get. DARKLIght will literally rip through a frequency like you just saw here and show us what's on the inside. As we narrow the light and we zoom in, it'll even change it then, because we're narrowing the focus of the whole image when we zoom in. When you look at this image right here, you see these up and down rays. They appear in certain frequencies, really, really intense frequencies, and it appears to be a form of gamma or radio waves. It could even be gravitational waves, but it's definitely energy because there's a pattern to it. And these patterns have to deal with spectrographic patterns and the way that energy and electricity shows up when there is waves involved. And they mimic sawtooth patterns and all these other features, which I found that happen in sound, which is another form of energy. And they do the same things as the color energy does, but they do it colorfully. So let's go in a little further. We'll drop the whites down, because we don't need, and as you can see the sawtooth pattern show up again. They go away as well. So if I dehaze this out some more, it's not as strong and precise. If I take the clarity down and then dehaze it again, I can get a completely slightly different look at it, but it will show up, and the more intense I get it, the more it will do once it processes it. I've gotten some of the images to a point where I can slide the black and white back and forth, and it will generate these lines. They literally pop up and down, and they're moving. And I've asked, and they, if you notice right here, they pass through it, and then they come out the other side, which is just a portion of energy and spectrographic patterns, because over here they're sawtooth, but over here they're not. So this one's smooth, this one's not. So there's actually a pattern of energy here. And when you go in and you zoom in on some of these things, you see, well, there's objects in here as well. These are small stars. This is secreting out this way. This is a small vortex. If we want, we can go in, hopefully it won't zoom out. We can stay right here close. Take this color range on this mask. select, and you're noticing the two red dots down below. So there are objects in rotation around this. So we've gone even deeper into this image, but now we're going to light up this dark area. We're going to see what's inside here by just simply using the gradient effects of dark light and how they fill in the overlays. So as we refine this, and then drop this mask down just a teeny bit. So that was amazing. So there's a lot of movement just in this image alone. Let's refine the mask down a little bit more. And we'll wait for this to catch up for it again. Let's go. Bring the texture down. Bring the clarity up just a little bit. Diffuse just a teeny bit. But I'm more concerned with the refinement of this color range, limiting what we can see here. Exposure down just a smidgen. And then we'll wait for this thing to finish processing. I've waited sometimes, just so you know, I've waited minutes for this thing to process. And it really is processing it. There we go. Excuse me. So there is a lot going on, as you can see from the pixelated patterns, which looks like fire. But we're going to quickly jump out and see what that looks like. Oh, that's kind of cool. So it's starting to peel into the outer edges as we bring the focus of the filter to the center. And this right here, I mean, I could stop right here and spend months examining this image. It's what it does. It's what DARKLIght does as a system. I'm going to export that little image. And then I'm going to save this as a particular version. Just going to call it inside 7. And we'll stop the video right here. But I've shown you what I do with DARKLIght and how it works. And we can continue going deeper down into that hazy area if we want. We can stop right here, go to another DARKLIght filter, and see what effects it has on it, like choosing Dark Night. And we'll let it go auto. And we'll see what it brings to the set of layers. So it's showing some intricate artifacts inside there. Let's see what CBE does. And I call that cosmic background energy. And so it's definitely showing more debris fields around the object. There's some very large outbursts of energy, and there seems to be some pulling coming from the dead center down 90 degrees straight down. So let's see what else we've got in there. We can go over to New Bright, which is a whole completely different series. It's based on the James Webb and the detail that it's capable with its IRC camera. It usually gives us a completely different look on things. And in this case, it did. And so we're going to select this, and it pushed the depth deeper into the center while providing a new view of the inside so that it breaks down the objects. And New Bright is adjustable, so we can adjust this a little bit depending upon which way you want to go with it, and it will adjust the tones up and down just like that. So the proof is right there. The filter works very, very well. We can undo that adjustment there and go back to where New Bright saw right there. And then we can zoom into this area right here in the beginning and kind of see what's going on. So I'm noticing over here that you have a tube that matches this background right here, and it's going down inside here to the back. This piece over here is acting as a input. When you look at some of these things, they act like inputs and outputs, like one's taking matter in and the other one's spitting it out. But in some cases you see a full torus, like a whole tube, and some of them even look like Mobius strips, but they're tubular strips. And you see that mostly in star rays. You see Mobius functionality within there, because it's constantly spinning. There's a math formula with pi, and it's just pi as it's spinning. And it's a real beautiful thing to see. But the circle here is just absolutely round and precise, and the density of this image is just harrowing. So you can go in here and you can look around and focus on certain processes that are going on and examine your images. You can do deep imaging. And if you want to take this to a completely different realm, I'm going to show you right now while we've got the video going. And hopefully my cold won't get in the way. But I'm going to take you, in the viewer, into the new STARLite edge process. So export that, open up Google, and go into my handy dandy folder where I keep stuffing everything under the sun. It started off as one thing that I downloaded from GitHub, but then I created like 40 other items and just kept going and going and going beyond this, because all I wanted was a small template. And I blew that out of the water and went with something even better. So we're going to go into index, and let's just do it Oops. As you can see, yeah, the Rydberg formula is amazing. Let's just go with index for now. I'm not going to show you char 7 plus. I'm just going to go right here. And so we, this is the latest image. And it's going to open this thing up. This was one of the first ones I did. I don't want to do that one. Let's see what we can find. Let's see that. Aha, there you are. Oh, okay, so number 5 is what we want. So we hit OK. And so this is what we were just working with. And so say you want to find out more information beyond all of this, especially this. So what it does is it uses the char energy edge detection, and it separates out the edges so that you can see. But what it does is it provides a depth system, almost like a depth map is what I built into this. And I separated out the depth map functionality in this so that you could just see the depth, and you could see the edging and how dark and deep it is. So I also gave it neon capability and added the Manhattan distance functionality in here. So going back to char, we can then take this image, and what looks like a mess to some, they'll know immediately what it is, but these little circle dots are stars. And not all of them are stars. Some of them are just big objects. So we're going to save this, and save that to here, and that's number 5. I'm going to use my ASM, which I always do, so I can separate that out, hit save, and now I'm going to stack this image with the original. And what it does is a really neat trick for visualizing the data. It takes what's in the image and it adds the intense edge to it so that you can see where in the image those edges were done. So we're going to take that, separate this out once it's done rendering. See right here, I'll call that A, and then we'll go in to Finder, pull up that image here, and take you into it. So now we can go in and kind of take a deeper look at how these images, you can see the waves in this, how it's flowing around. You can see the gradient movements down here and how deep this is. And in some cases you can see movement and swooshes in this direction. But with this image from this distance, it'd be really hard to tell. Some images will show up immediately, but there are component pieces within there that are all the same. You do see the little plus signs, and those are usually stars at the center spinning. But in the case of this, I'm still perplexed. I need more information. Although I am seeing the same color tones over here as I am over in this massive monster, I'm still not getting which way one of these is going, or whether they are just kind of spinning around the center of this. So further investigation will take place in this. But you can see just how detailed some of these formations get and how elastic it looks. This is all energy in most cases that is being recorded, and it's simply recording the activation of matter in the photo itself that it took out in the universe. It recorded the energy, but it was beyond the visible spectrum. So you've got infrared, gamma, beta, all sorts of X-ray, and it just is what it is. And the way the math formulas were done in the edge system, it was designed to do exactly this. Find electricity, find all the matter that it can, and display it for the user. Is this thing? Oh, okay, let's see what this one does. So I did have it loaded. So let's go. I'm going to take you back to that one. So this is with the filter that I had built for depth, and depending upon which one of these I choose, I think sharp 7 is like really edgy. Yeah, it breaks apart everything. So let's go with the 6 grid and take a look at this. So there's a star and a void in the center isn't lit up at all yet. But that's okay. Whoop. Hate it when it does that. Yeah, it's not very smart. Yeah, I broke it. One more time. Let's see if we can brighten it up in Manhattan distance. So it's a little brighter, but you can see the formation of stars and how the energy wraps and flows from the center out. And I'll show you that math problem later on, not in this video, but in another one. It's out in the wild. That's spectacular looking. So there's several very large stars just within this small area. You can see by the T's. And there's a star here. There's a star here. And there seemed to have been a star that exploded, collapsed, and went in, which is what they seem to do. And they do it quite frequently. They build like a nearby black hole that it too starts taking in all of this. But whether or not this black hole is attached or communicating with this black hole, it's hard to tell. But the distances don't matter. I've seen it, seen some really long distances connect to one another, light years across. So it's going to take a lot of investigation on a lot of scientists' parts once they get their hands on this, because it really does make a difference in what you can do and see inside. One more. So we did 5. Let's try out 4. So this one, this image, we had worked our way up to a certain point, and I'm still curious about all that. I love this inner formation though. And yes, this is an inverse square, and yes, the circles form in the center. I've seen that one thousands of times around the universe. Alright. Oh wow. So that's a whole other different view, and we're registering electric activity. So that is a brilliant little tuck. So that's where the blue light was coming out in the beginning when we looked at it in the previous image. Right there. So that little sliver is an actual galaxy on its side right here, and it's spinning, and this one's being torn apart, but this guy is part of a collapsed star. You can see where the jets were, and once we get into the detail on this, you'll probably have arms coming out here that created these guys, and you'll see them. This looks like one. So arms break off, and they form these huge pieces of electrical and solids that tend to show up quite normally, like these weird things. And they're usually broken apart pieces of the original star. They all match the exact same color, and they tend to share and blend and bend and tear apart as they're basically being ground up inside the spinning of the outer areas of a galaxy, such as M87. So more research would need to be done, but here's a perfect example of a star that is in the center, and what it's causing to have happen around here. And these mirror the larger ones is one thing I've noticed, and I was trying to find the research on it, but it looks like I can't zoom out anymore on this. But the similarities between the little guy and the big guy are usually quite daunting. Oh, look. Hello, Dave. I'm here. Creepy. So, there you go. You've seen the processes that I do. You don't get to see behind the camera or anything, but you get to see what I work with when I'm developing these processes. And there's more to come. We're at like image 9,000 for the year 2023, and the more photography that NASA, ESA, NOR Labs, ESO, Chandra, and all of them provide, the more data we can throw at the dark light process. And from there, it's just a matter of sorting and snorting, as we say, and figuring out what's what and finding patterns within the universe, because there are lots of patterns out there. And I just wanted to, hopefully, if the recording and everything on this is correct, and I'll play it back, I'll post this video for you, and you'll get to see what we just did. My name is Kelly Swenson. I'm a citizen scientist, and thank you for watching this episode. Have a great evening, and don't forget to look up at the stars.